This video is about strong acid and strong base titrations. You should already be able to calculate the concentration, pH, or K of any acid or base. But by the end of this video, you should also be able to describe titration setups and their purpose, read and explain strong acid-base titration graphs, and calculate pH at any point during a strong acid and strong base reaction. So the question of the video is, when we do our labs, why is it so important to titrate slowly? So there's a lot of memes out there about getting to your endpoint of your titration really slowly, because one drop will send you over the edge. So titration definitions. It's important you write these down. A known concentration of a base or acid is slowly added to a solution of an unknown acid or base, determines concentration in a titration. If you were in Regents Chem, you've already done something like this and you've already talked about what a titration does. So if I know the molarity of one thing, I can use the other one to neutralize it and find its molarity. This is also known as standardization if it uses a primary standard. So let's talk about those words. A primary standard is a solid where the moles are constant. I know exactly how many moles of the solid acid I have because I weighed it on a balance. Whereas if you were talking about a molarity of a solution, the moles will, be variable based on if you left that solution out in the atmosphere. Because you might have dissolved a certain amount of moles, but you added a certain amount of water to that, and as the water increases or decreases by evaporating or condensating into the container, if you leave it open, it will change the molarity of the solution, it will change the liters of the solution, and everything in your lab will be kind of off because of that change in water. So then you won't actually be knowing exactly how many moles you put in there. So it's better to first titrate with something that's solid because it's not going to change with atmospheric conditions. And so if you're standardizing something or finding its molarity, the best thing to do is find it with a solid, so titrate it against a solid. So the titration methods is basically you use this long burette and you put a known substance inside the burette and an unknown substance inside your Erlenmeyer flask. And you'll either use a pH meter or indicators to identify when you've neutralized it. So in the first lab, what we'll do is use phenolphthalein like we did in Regents Chem to determine its equivalence point, or the point where you neutralize the acid and the base. They're equal in the amount of acid and base that you've put in there. So the titration will happen and will be colorless the whole time on the bottom because we'll have an unknown amount of acid on the bottom, and we'll titrate with the base that we do know, and eventually it will turn pink and you'll notice stop because that's your endpoint where the indicator changed color. At the endpoint, you're hoping it's also the equivalence point. The problem is when you use phenolphthalein is the endpoint's actually at 8 when the equivalence point should have been a pH of 7, right? So it's not exactly perfect. The lab will be a little bit off. It won't be that far off, and we'll see by the end of the video that it won't be too bad. But we can use other indicators such as like thymol blue or something like that, or in a separate lab we'll actually use a pH indicator, probe, to see the pH as it goes. So that'll be pretty neat. The equivalence during a titration. So at first you'll start with 2 clear solid solutions. You'll put a little bit of phenolphthalein in, and as you pour the solution in, you'll see little drops of phenolphthalein, but you don't want to stop. You want the entire solution to be pink. So you continuously swirl your solution and add your sodium hydroxide until you get a light pink. If you get a dark pink, it's too far. Once you've done that, you'll use the molarity equals moles over liter formula, or molar times volume is going to give you moles because you're just going to cross multiply. And you'll also know that the moles of acid equal moles of base because that's the whole reason you titrated, was to neutralize the acid and the base. And from that information, you should be able to determine the molarity of an unknown at the equivalence point only. So only at that one part of the lab. If you go too far, again, this is equivalence point only. If you go too far, you can't actually calculate this appropriately. So here's an example of what we're looking at. An unknown concentration of sodium hydroxide was found in the stockroom. It's measured with 20 milliliters of 2 molar hydrochloric acid in a flask and added a few drops of phenolphthalein. I filled a clean 50 milliliter burette with the unknown sodium hydroxide and began the titration, slowly adding sodium hydroxide dropwise until a faint pink color appeared. Initially, the volume of the base read 0.15 milliliters, but as the titration was complete, the volume reread as 35.45. What's the concentration of the base? So what we should do is start with the amount of acid we know. We know that we have 2 molar acid, and we know that we use 20 milliliters because we pour that into the container. So if you multiply those two parts, we know we have 0.04 moles of hydrochloric acid. What we're doing is we're adding base until that hydrochloric acid is completely neutralized. It's not there anymore. It's not going to change litmus paper red, it's not going to irritate your skin, and so on. So if we do it appropriately, we will stop when the moles of equal acid equal the moles of base. So we'll also have 0.04 moles of base. To find molarity, we just need to know the volume of the base. We can do that by ignoring the 50 milliliter burette. That's just the apparatus you're using. You're looking at the two other volumes. We started at 0.15 and we dropped it out until it went to 35.45. So what we'll do is we'll subtract those two volumes to get 35.45 minus 0.1015. I put it into liters, so that's moles per liter, so it was milliliters. And I subtracted them, molarity divided by the subtracted volume. And if you do that, you get 1.3 molar. Right? So now we know the molarity of the base. Or if you took Reagents Chem, you might know about the MAVA equals MBVV formula, which works just the same, 2 molar times 20 milliliters, so I noticed I didn't change it to liters, equals unknown molarity times the volume of the base used. So you still have to do the subtraction, but it can be in milliliters, and you get the same answer. The thing about that MAVA is most graders don't want to see that. You're more sophisticated than that now, and you should be using the first way I showed you. Also because this only works if the acid is monoprotic, has one hydrogen, the base is monohydroxic with one hydroxyl group, and that they're both strong in this case, right? So I don't want to use MAVA for most conditions, and so it's more important to use a long method because it shows that you understand the moles are equal and how to do a molarity formula. When we use the pH probe, we'll be able to see pH curves that kind of look like this. What it shows is at the start of the titration, you have mostly just acids, so the pH is pretty low, and you added no titrant or base. And as you increase the amount of base you add, the pH slowly goes up. Eventually, you'll hit the equivalence point. The reason I know it's equivalent is because the pH is 7, so there's no extra acid or base, and it's strong acid base right now. And so anything below it was when you had too much acid, and anything above it was when you have too much base. So just before and after the equivalence point, the pH is increasing really rapidly. So this is one of the reasons why we want to go nice and slow around there, because a few drops might be the difference between a pH of just under 4 and a pH of just over 10. But we're going to prove it some calculations in a few moments. So remember, the titration of a strong acid and base shows the equivalence point where moles of acid equals moles of base, and the pH would be a 7 at that point. So what we're going to do is we're going to see a lot of these graphs over the next couple weeks. You should be able to pick out a strong acid, strong base titration pretty quickly because its equivalence point, or the steepest part of the graph, is exactly at 7. Once the concentration is known, the pH should be able to be calculated at any point. So this was generated probably by a pH probe, which we'll use eventually, so a device that was put into the solution to measure it. But you should also be able to measure it and calculate it on your own. So here are the steps. 1, write the reaction, a single-headed arrow if the species are both strong. 2, start an icebox with initial values, but this time in moles, because we're not worrying about equilibrium right now. We're going forward in a forward reaction, right? Single arrow. So you can stay in moles. Determine the change in mole ratios. Remember, the x will be equal to the lowest initial value. So you'll say this amount of acid reacts with this amount of base and makes this amount of salt and this amount of water. That x value will be the same across, and it will be the limiter, or the lowest value that you have given. And 4, given the determine the equilibrium values by subtraction and addition, like literally calculate it. If a strong acid or a strong base is left over, divide the leftover amount by the total volume, because remember, you're in moles right now. So if you divide by total volume, you get a molarity, right? If you just keep it in moles, you can't really do a lot with that. And to calculate the pH, you just negative log the molarity of the hydrogen ions, or the hydronium ions. So remember, this has to be a concentration because of the brackets. So that's why we had to divide by volume. Again, these are in the same container when you're titrating, so that's why you need to have a total volume. It's in caps. You should probably write it down. So let's try these 6 steps in order. Calculate the pH when 25 milliliters of 0.1 molar hydrochloric acid is titrated with 10 milliliters of 0.1 molar sodium hydroxide. I can kind of already tell, because I gave you an easy example, that there's extra acid left here, right? Because they were both the same molarity, but there's a little bit more volume of acid. So I'm expecting the pH to be low. It's not always easy to identify that, though. So what we're going to do is the same steps that we always do. We're going to multiply the volume times the molarity to find the moles of the acid, and the volume and the molarity times multiply those to find the moles of the base. Once we know that, we set up an icebox. The hydrochloric acid reacts with sodium hydroxide to form salt and water. The initial conditions were the 0.0025 of the acid and the 0.001 of the base. Normally in the change, what you would do is subtract x, add x, and add x. But what we're going to do is go a step further. Not just write those x's, and if you really want to, you could. But remember what we said the change was going to be. It was going to be the limiter of those two numbers. So the lower number of the two. So I'm going to subtract 0.001 from here, and I'm going to gain it in the products. Which is why I know I had an excess of hydrochloric acid. If I had subtracted 0.0025, I'd had a problem here, because I would have a negative amount of base. That can't happen. So remember, you're always subtracting the lower number. This will tell you how much you have left over. Some people can do this in their head. I'm just trying to show you something that will work every single time, even if we have weak substances. Once you know how much acid you have left over, we're going to icebox that acid. But first, remember these are moles. So we're going to do 0.015 divided by the total volume. So the 25 milliliters and the 10 milliliters, which is 35 milliliters, or 0.035 liters. And then negative log that value, right? Because pH. We get an answer of 1.37. So this looks a lot like the way that we set up weak acid bases, because we don't really know what we have in our solution, right? It has a very similar feel. It should have, anyway. So let's try it one more time. Calculate the pH of 25 milliliters of 0.1 molar hydrochloric acid, titrate with 25 milliliters of 0.1 molar sodium hydroxide. So when you multiply the molarity times the volume, you'll get the moles of acid. Same thing with the base, right? And you'll put it into your icebox. So these were the same because they're the same values. When you subtract, you'll notice that you'll have no acid and no base left over. You only have salt and water. Because the salt was formed by a strong base and a strong acid, your pH just happens to be 7 because you had a neutral salt. So using some rules from before, right? So that was a nice, easy one. We're going to do one more and guess what you think it will be at the end of the titration, right, where you have too much base. So calculate the pH when 25 milliliters of the 0.1 molar hydrochloric acid, which if we multiply, we'll get the moles of the acid, is titrated with 35 milliliters of the base. So now we have too much base. We can kind of tell, but let's just put the calculation out there, right? Molarity times volume. And then write our equation that hasn't changed. Put in our initials. And then our change. Our change will be 0.025 this time because it's a smaller value. It goes across the board. You subtract from what you have and add to what you don't. At equilibrium, you'll have no acid, a little extra base, and then the salt and water, which are neutral. So that base will drive the pH. You'll negative log the base's moles, remember this is moles, divided by a total volume. So remember, I total the volume here. And the reason I've subtracted from 14 because I was expecting a basic number, right? So I'm at 12.22. So what you've noticed in the three examples we've done, the three types of examples where you have too much acid, neutral, or too much base, is everyone starts at the same. Find your moles, subtract your moles, and then find your total molarity to find a negative log. So the question of the video is, why is it so important to titrate slowly? The equivalence point of is pH of 7, right, on this graph, is showing that it took 35 milliliters of titrant. I'm assuming that sodium hydroxide, we're going to also be given that it was a 1 molar solution. And it was neutralizing 20 milliliters of an unknown acid. What's the concentration of the acid? So the first thing I would do is multiply what I do know. I do know I have 1 molar of base times 0.035 liters, and that's how much base I have, 0.035 moles. What I also know is that's also how much acid I have, because at equivalence, moles of acid equals moles of base. So what I can do is divide by the acid that I used, 0.02, and this will give me the molarity of the acid, 1.75 molar. Right? So this is the first part of the video that we talked about. But what's the pH if I use 34 milliliters? So I want to know what's the pH, just one drop, 1 milliliter, too less than you're supposed to have, right? Just 1 milliliter off from what you should have. So in this case, we know everything. We know molarity, we know volumes of both, so we're going to multiply both. Again, 1.75 was given, was known as the molarity of the acid from the previous question. I know I used 20 milliliters of it, or 0.02 liters. This is how much acid I have in the solution. I was given that it was a 1 molar solution, and I used 0.034 milliliters this time, liters. So that means 0.034 moles of base was used. You could write this into your icebox, where some people are starting to realize you just subtract them to figure out how much strong acid you have. So I have 0.001 moles of strong acid left in, and remember we add our volumes to find the total, because we have a total solution, they were added together. And once we find the concentration by dividing, we just negative log that concentration to get a pH. So some things I want to point out is the pH is significantly lower. Here, up here, the pH was 7. 1 milliliter down, the pH is 1.73. So that's really why we want to go slow, because the pH drastically changes if you just change by 1 milliliter, right? Also, so 1 drop will do the same thing. Also, I want to clarify the 2 types of questions we've seen. So we saw a question where we didn't know one of the molarities. And then we saw a question where we knew everything. So the one when we don't know the molarities, we find the moles, and we find moles divided by its own liters. But when we know both, everything, we find the moles, subtract, and divide by total volume. And that's important to know the difference. At this point, you should be able to describe titration setups and explain their purpose, read and explain points in a strong acid, strong base titration graphs, and calculate pH at any point during a strong acid-base reaction.